If you want a little more practice in setting up these integrals for your moment of inertia calculations, this is the video for you. We're going to look at this problem. I want you to go ahead and pause the video, look at this problem, and evaluate this shape that we have here, y equals 2.5 minus 0.1 x squared. Evaluate that for your moment of inertia about the x-axis and about the y-axis. Just set up those integrals. You don't actually need to evaluate them, just getting practice delineating those slices, whether you're going to slice it in the dy direction or the dx direction. Practice taking the slices and pulling out the information that you need so that you can set up the integrals correctly. So go ahead and pause the video here, and then we'll go through all 4 versions that you can do to set up these integrals. So we're going to look at taking a dx slice first. So we'll look at taking a vertical slice first, one where the width is dx, and we're going to do the x and y for this scenario, and then we'll do the dy scenario. I've got timestamps if you want to check all of your integrals at those times. So we have our dx slice. This is the one we're going to look at here. You have to choose, your very first step is always choosing whether you're going to take a vertical or a horizontal slice. So in this case, we're going to take this vertical one, which means that our equations are going to be for our x, we're going to be using parallel axis theorem, right? Because it is perpendicular to the x-axis, we have to use parallel axis theorem for this dx slice. So this is ix prime plus a d sub y squared. And then for our y equation, a slightly different color, moment of inertia about the y-axis, we're going to use the basic integration equation. Our basic integration equation is our x squared dA. Now that we have our 2 equations that we can use with this dx slice for our moment of inertia about the x-axis, moment of inertia about the y-axis, now we can pull out the information that we need. Right, so the info that we can pull out from this, again, we have a dx slice. The height of this slice here is going to be the y value. And the location is our x value. Right? So what other information do we need? We know dA, right? dA comes from that slice there. dA is going to be y times dx. Y times dx. So we can insert that in here. And if we do that, let's go ahead and do our IY first, since that's the simpler one. So my moment of inertia about the y-axis is going to be the integral. And again, it's across this whole distance here. So down from the left all the way to the right side is going to be from -5 to 5. X squared y dx. And of course our integral is in terms of x, which means we have to substitute in this y equation that they gave us. We're going to put that in to the y in here. So our moment of inertia about the y-axis is the integral from -5 to 5 of x squared times 2.5 minus 0.1 x squared dx. So that's one integral we can get, right? And we can also get our moment of inertia x. So the components that we still need for that one, we need our moment of inertia about the centroidal x-axis. Moment of inertia about the centroidal x-axis, which we pull this from a table, right? This is for our rectangular slice. So it's this red slice here. It's the moment of inertia for each individual differential slice. And so I pull that out from my table, and that gives me 1/12 base times height cubed, which in this case my base is going to be dx, and my height is going to be y. So 1/12 y cubed dx, right? So I'm going to have to be integrating this term. I'm integrating this term, and then I need to find my other term as well. Right, we can also write this as this, dA. We know what dA is, we already found that. Now we just need our dy term. And this d sub y term, again, is the distance from the axis of interest to the centroid of your little differential slice. So it is this distance here from the axis of interest, which in this case is the x-axis, right? So it is the y distance up from the x-axis to the centroid, which we've seen before as y tilde. In this case, this distance here is y over 2. If I plug this into my equation, I'm going to get y sub x is 1/12 y cubed dx plus y dx times y over 2 squared. Again, I need to finish setting this up in integral form with everything in terms of x. So I'm making those substitutions now. So I have the integral from -5 to 5 of 1/12, then substituting in my x, 2.5 minus 0.1 x squared, all cubed dx, plus, and then substituting this in, I can rewrite this term as a y cubed over 2. I'm going to say this is 1/2 times 2.5 minus 0.1 x squared, all cubed dx. All right, all of this is one integral evaluated from -5 to 5. So this would be my second integral. And again, part of the point in this is figuring out which integrals are going to work best for you if you have to integrate these by hand. I'll say for your homeworks and everything, you don't have to integrate these by hand. Do it if it is an easy enough integral. It'll save you time if you're just integrating, x squared. That's faster to do by hand than to type it on the computer. But if you have something extremely long like this, where you're going to be doing multiple substitutions or chain rules or things like that, it's totally okay to save yourself some time and just put it into an integral calculator. It's a little bit harder to check the calculator if you make a mistake if you're not doing this by hand, but it can save you some time and some of your own math errors if you just plug it into a calculator. I would really recommend at least double checking yourself with a calculator. So now that we have these two integrals, let's check the other way, right? So what if we took our differential slice as horizontal, right? So horizontal through this entire semicircle shape. Got it there in the purple. Now everything is flipped. Instead of using parallel axis theorem for my x, I'm using it for my y. And I'll use the basic integration equation for my x. So for these, I'm going to delete all of this. Now what I have is I have my moment of inertia about the x-axis uses the basic equation. So y squared dA. And my moment of inertia about y uses the parallel axis theorem. So finding this moment of inertia y prime, moment of inertia about the centroid of the shape, plus integral dA dy squared. So now we need to pull out our information for this. We could clean this up a little, remove my red guy, so we can see what's happening with this purple differential here. So I'm just going to get rid of all of that. Okay. All right, so I've got this purple guy. He goes all the way across. All the way across here, where my differential slice is now dy. So let's look at the components that we need, right? I need dA. So my dA in this case, we know the height is dy, but the width here is this entire length, right? This entire length here. We know the length from the axis, right? The y-axis to here is x. But notice it also goes the same in the other direction. This distance is also x. So now for us, our dA in this case is going to be 2x, right? For each side of the x-axis that this is on, times dy. So that's our dA term. The other terms we need, we're going to need our this is not dy, this is dx. dx, there we go. So we need that dx term, distance to the x centroid. Right, so what is the distance to the y from the y-axis to my x centroid? Where does my x centroid hit for this bar? Where's the centroid of this thing? And if we look, we notice this thing is totally symmetrical about the y-axis. Our centroid for these horizontal differential slices that we're taking are always going to be on the y-axis itself, right? It's actually never changing since this is symmetrical about the y-axis. So the centroid of this is 0, right? There is no distance between the y-axis and where the centroid of the bar is. So this is actually a big old 0, which means we don't need to worry about this term at all. So now if I go to set up these equations, my moment of inertia about the y-axis is the integral over my y values here. So from 0 to 2.5, y squared, and then my dA is 2x dy. If I rearrange this x equation here, I get y over 2.5. Oh wait, no, that's not right. Sorry. I get y minus 2.5. Y minus 2.5 over negative 0.1. And then I take the square root of all of that. So that's my new x term. So I have to plug that into my integral. So it's the integral from 0 to 2.5 of y squared times the square root of y minus 2.5 over negative 0.1 dy. So that's my moment of inertia about my x-axis, and then I'll go ahead and do my moment of inertia about the y-axis from parallel axis theorem. So again, same integration limits because of the dy slice, right? dy, so we integrate over the y. And then I need this iy term, which if I pull that out from my table, moment of inertia of my centroid is 1/12 height times base cubed. Or in our case, the height is dy, and the base again is 2x. So here I've got 1/12 times 2x cubed dy. And there's no secondary term for that. So this is the entire thing that I'm going to plug in my equation. So it's 1/12 times 2x cubed dy. And again, I would have to make that x substitution in there. I'm going to go ahead, let's just erase and pop it in there real quick. Erase that x term. 2 times the square root of y minus 2.5 over negative 0.1, all cubed, dy. And that would be my integral for my moment of inertia about y. So it's really about kind of strategically picking whether you want to do the dy or the dx, or if you want to do both and just use basic integration formula. It's up to you, and the easiest easiest integral to evaluate. So get some practice taking these slices, figuring out all of the components that you need, which primarily are your dA, which is given by your slice, and then the centroid, right? All of this is information you're pulling off of that differential slice that you're picking.